So to finish up our introduction on electromagnetic theory, we're just going to talk about real heavyweight in terms of electromagnetic theory. And this is a gentleman, his name is James Clerk Maxwell. Now, before we get to him, we just want to recall some important things that we talked about in the last unit. So we talked about Hans Christian Ørsted, and he was the one that discovered an electric current can produce a magnetic field, or if we want to be more formal, a changing electric current will generate a changing magnetic field. And then Faraday and Henry, they proposed sort of the opposite process. So we had that changing magnetic field will produce a changing electric current, or more formally, a changing electric field. Now, those two processes, electricity and magnetism, people up until the mid-1860s thought they were separate processes. A gentleman named Maxwell, he linked those two processes together. He very much said electricity and magnetism are related. This is where we get that whole concept of electromagnetism. Now, Maxwell was a very, very, very smart person. So he used some ingenuity, some really advanced math, and he was able to take all of electromagnetism and to condense them into these nice, beautiful four equations called the Maxwell's equations. Do not, under any circumstances, memorize these or know these. These are well beyond the scope of high school. I just put them here for good measure. But if you take any electromagnetic radiation or electromagnetic theory courses at the post-secondary level, you will run across these. So Maxwell, in his equations, he made 5 predictions about electromagnetic waves and their properties. So first of all, he hypothesized that an accelerating charge will produce electromagnetic radiation. So that's good. We know that that's correct. And the reason for that happens to be that when we have this accelerating charge, it's going to produce a changing magnetic field, and then that changing magnetic field is going to produce a changing electric field. But then that changing electric field produces a changing magnetic field, and you kind of have that cyclical process. A changing electric field generates a changing magnetic field, which generates a changing electric field, and so on and so forth. So this is also why we refer to electromagnetic radiation as self-propagating. So the frequency of oscillation of the charge that's producing this radiation, it's going to correspond exactly to the frequency of the electromagnetic wave produced. We also know that's correct. So Maxwell, the only real flaw in his theory, he predicted the speed of light to be about 3.11 times 10 to the 8 meters per second, and it obeys the universal wave equation. So he was kind of partially right. It does obey the universal wave equation. His speed of light is a little bit on the large side, but we have to forgive Maxwell a little bit. This was done in 1865, so given the technology of the day, I'd say he did a good job. So we got to cut him a little bit of slack on that. And then we also know, and Maxwell predicted, and we know that these electric and magnetic fields, they're always going to be perpendicular to each other. And this is really important. And then those fields, the E and B fields, they're also going to be perpendicular to the direction of propagation. So what we would generally say is we'd say that the electric field is perpendicular to the magnetic field, which is perpendicular to the velocity or the direction of propagation. All 3 of those fields are mutually perpendicular, and that's a really important theory point that comes up on the diploma exam, and I'm going to talk a bit more about that in a moment. And then Maxwell also predicted that electromagnetic waves, they should be able to demonstrate phenomena like interference, diffraction, refraction, and polarization consistent with transverse waves. That one we're going to talk a lot more about in this part of the unit. So here's an electromagnetic wave, or at least like a basic sketch of it. So we have that changing magnetic field that's that changing magnetic field that's being produced, which is producing this changing electric field. And you'll notice that at all times your magnetic field is perpendicular to your electric field. And then perpendicular to these 2 directions, we have this direction of propagation where the wave is heading. Now, with that said, we can determine the direction of propagation if we know the direction of the electric and magnetic fields. So there is a hand rule for this. If you do any EMR field studies a bit later, you'll talk about something called a Poynting vector. We're not really interested in that right now. But what we could do is we could use our right hand. You could place your fingers in the direction of the electric field. You can place your open palm in the direction of the magnetic field, and then your thumb will point in the direction of propagation. Now, that's one way to do it. That's not really the way you'll probably be asked to do this on a diploma exam. What's most likely going to happen is they're going to give you planes of oscillation. So for example, let me draw a coordinate axis here. So like if I kind of drew, let's say that's an x-axis, that's a y-axis, and then sort of in and out of the page is a z-axis. So what they may ask you is they may say, okay, in my x-plane, here's my electromagnetic or my electric field. In this z-plane or in this y-plane, here's my magnetic field. So I have E in the x direction, I have y or E in the x-plane, I have B in the y-plane. So what they may ask is which one of these three planes are you going to find the direction of propagation? Well, all of these have to be perpendicular to each other, B, E, and V. So if the y and x planes are already occupied, that's telling us that the direction of propagation would have to be in the z plane. Now they're most likely not going to ask you is it positive z or negative z. All you really need to know is that it's going to be in the z plane. And this all comes from that important point that the electric field, the magnetic field, and the direction of propagation or velocity, they're all at 90 degrees to one another. They are all mutually perpendicular. What that means is E is perpendicular to B and perpendicular to V, and B is also going to be perpendicular to V. They all have to be simultaneously perpendicular. That is the key important point. They ask that on the diploma very frequently. Now, Maxwell, when he proposed his equations, this was theoretical. Now, a lot of times in physics, we've proposed theory. We have to wait for the experimental part to catch up. So it took a while for that to catch up. And in 1887, Heinrich Hertz, he did a little bit of an experiment to produce and detect EMR. So what he had is he kind of had this apparatus here. And what was happening is that between these coils of wire, what was happening is a spark was being produced. Now, this spark, when it jumped across this gap, this would produce electromagnetic radiation. Now, what was happening is that electromagnetic radiation was propagating in all directions, so it would have propagated towards this antenna here, and this electromagnetic radiation would have been picked up on this antenna. Now, what Hertz had found is that the frequency of this electromagnetic radiation produced at this point here, that matched what we'd say is that frequency of oscillation of the antenna. So the frequency produced and the frequency picked up, they're exactly the same. So Hertz established evidence that he established the first real evidence of the existence of electromagnetic radiation. And he did this with radio waves. Now, kind of funny, people asked Hertz what were going to be the big applications of his discoveries, and he pretty much just kind of said nonchalantly, well, nothing, I guess. Good thing he was wrong on that one. Well, I shouldn't say good thing he was wrong, but he was definitely wrong on that. As you know, electromagnetic radiation is a huge part of the modern day world. I don't know where we would be without our studies of it. So Hertz, sorry buddy, you were wrong on that one. Your discoveries had huge applications, and that's what we want to study for the next while.